In this lesson, we will learn about stellar variability. So, a brief outline of my talk is first of all, I will be talking about variable stars and what are variable stars, light curve of a variable stars, importance of variable stars in modern astronomy, and then after that I will go into the classification of variable stars. I will describe the broad classification of these variables into two classes, mainly the intrinsic variables and extrinsic variables. And after that I will be talking about the pulsatile stars, which are one of the classes of intrinsic variable stars, and then I will go into the details of each of the pulsating stars, and lastly I will be talking about the eclipsing binary stars, where the variability due to eclipses, and these are extrinsic classes of variables. So, first of all, let us learn what are variable stars. Variable stars are stars which change brightness over time periods ranging from a few seconds to several tens of days or even years. A plot of brightness variation expressed in magnitude with time is called the light curve of a variable stars. The time is generally expressed in Julian date, which is the interval of time in days since noon at Greenwich on January 1st, 4713 BC. A regular variable star can be characterized by its light elements. They are its period and a reference epoch. The epoch will be given in Julian date and the period will be in days in most cases. Mostly a light curve is expressed in terms of a phase light curve, where the phase is the fraction and it goes from 0 to 1. It is a fraction of the period at the time of the observation. Phase is defined as t minus t naught divided by p minus the integer part of t minus t naught divided by p, where t is the time of observations and t naught is any reference epoch like maximum or minimum of a light curve, and p is the period of the variable star. This p is found from the light curve of variable stars. So, here is one example of the light curve of an eclipsing binary star, and in the upper panel we can see that the star has been observed in 3 days, and now we will try to convert this light curve into a phase light curve. So, for that we will be using the equation, phase equation, just we have talked about it a few minutes earlier, and this phase is already we have defined, and the phase light curve is given in the bottom panel. Sometimes in case of a binary star, there is a called the ephemeris. Ephemeris it gives the timing of eclipses, and this is given by an equation. This is in heliocentric Julian date, and this is the time of occurrence of primary eclipse, and this is the any reference epoch at the time of observations, and p is the period and E is basically called the ephemeris. Now, we will be talking about the importance of variable stars in modern astronomy. Variable stars give important information about the nature and evolution of stars, the stellar populations and the structure of the galaxy. This information can be used to gain fundamental knowledge about our universe in general. Pulsating stars are used to constrain stellar models, to understand the internal structure of stars, and in determining cosmic distances. On the other hand, eclipsing binaries are useful for direct determination of masses and radii of stars using the geometry of their orbits. They also provide an accurate method for measuring distances, since the radii and temperature of the components can be reliably determined from the combined photometry and spectroscopy. Now, let us talk about the classification of variable stars. Variable stars are mainly classified according to the cause of their light variations. And they are classified into two main classes: intrinsic variables and extrinsic variables. In case of intrinsic variable, the variability is caused due to the changes in the physical properties of the stars themselves. This category can be further subdivided into three subgroups: pulsating variables, eruptive variables, cataclysmic or explosive variables. In pulsating variables, the star's radius alternately expands and contracts due to their natural evolutionary aging process. Most of the pulsating stars occupy a narrow strip in the Hertzsprung-Russell diagram, which is in short called HR diagram, running from upper right side of the diagram to the lower left at approximately constant temperature, called the Cepheid instability strip. Eruptive variables are those stars which experience eruptions on their surfaces like flares or mass ejections. And cataclysmic variables or explosive variables are the ones which undergo a cataclysmic change in their properties like nova and supernova. So, this diagram shows the instability strip in the HR diagram, where the pulsating stars, when they come inside this strip, they pulsate. The main stability regions are the Cepheid instability strip. This is the Cepheid instability strip, including its intersections with the main sequence. This is the intersections with the main sequence. This is the main sequence line, 0 age main sequence line. This region is called as delta Scuti instability strip. The region of coolest Miraz, coolest Miraz, and the region of beta Cephei and slowly pulsating B stars. There are also instability regions shown at the dotted line at the bottom of the diagram, which include the nuclei of planetary nebula and the DOB, DBV and DAV pulsating stars. Now, one of the important diagrams in astronomy is the Hertzsprung-Russell diagram, and in short it is called HR diagram. And as we have seen that that pulsating stars, when they are in the different evolutionary stages in the HR diagram, they are likely to pulsate. There are instability regions, and when the star enter into the instability region and leave the region, so while they are in the region, they pulsate. One of the important quantities in the astrophysical quantities are the stellar luminosity and the surface temperature. Hertzsprung-Russell diagram is a plot of stellar luminosities or absolute magnitude versus spectral versus surface temperature or spectral type. Now, here is a in the left panel HR diagram for all stars visible to the naked eye down to an apparent magnitude of 5 plus all stars within 25 parsec. Right panel shows a HR diagram of a globular cluster M55. Now, this shows the evolutionary tracks of the main sequence stars, and this shows we can see the different regions in the HR diagram. This is as you can see that when the star basically burn helium in their core to produce carbon and oxygen, this is called the horizontal branch stars. And in the main sequence, a star burns hydrogen to produce helium, and so similarly different tracks of nuclear burning are shown in the figure. In the main sequence, a star mainly burns hydrogen in the core. Now, stars classification is incomplete without luminosity classification. And this modern luminosity classification scheme is known as Morgan-Keenan luminosity classification scheme. Here stars are classified into different luminosity classes, like bright supergiants are classified as 1A, supergiants are classified as 1B, bright giants are classified as 2, giants are classified as 3, subgiants as 4, dwarfs or main sequence are classified as 5, subdwarfs are classified as 6, and white dwarfs are classified as 7 in the Morgan-Keenan luminosity classification scheme. For instance, Sun is a G25 star. So, here G2 is basically the spectral type is the, and this is G2 is the spectral class and 5 is the luminosity class, which shows that Sun is basically a main sequence star. Now, we will be talking about pulsating stars. Now, pulsating stars are classified based on their mass, evolutionary status, period, amplitude and shape of the light curves. Now, in the HR diagram, these stars are mainly classified into beta Cephei stars and slowly pulsating B variables. Then we have Rho stars, rapidly oscillating AP stars. We have gamma Toridas variables, delta Scuti stars. Now, all these stars, these 4 stars, they are located in the main sequence. They are located in the main sequence, and out of this, these 3 are Rho AP star, Rho star, gamma Toridas variables, and delta Scuti stars. They lie within the delta Scuti instability strip. Now, we have the RR Lyrae stars. RR Lyrae stars, they are in the horizontal branch, and then we have Cepheids of different class like type 1 or type 2 Cepheids. Type 2 Cepheids are in the AGB or post AGB stages of stellar evolution. These 2 RR Lyrae and Cepheids, they lie within the Cepheid instability strip. Then we have the Mira variables, which are in the AGB stage of evolution, and apart from that we have the pulsating white dwarfs which lie in the planetary nebular tract. Before going into the details of each of the stars, we will try to understand a few things. First, we would like to know what is an hydrostatic equilibrium. Hydrostatic equilibrium is very important equation for stellar structure dealing with spherical symmetric objects. It refers to the equilibrium conditions of the star when the force due to gravity is balanced by the force arising due to the pressure gradient of gas plus radiation inside the star. And mathematically, the equation can be written as dP by dr is equal to minus g mr rho r divided by r square. It is the pressure gradient dP by dr and not the pressure which supports a star from collapsing under its own gravity. Here P denotes the total pressure, mr the mass enclosed within the radius r, and rho r density at r. Now, here shows one of the cartoon, and which shows the existence of pressure gradient inside the star, which supports the star from falling under its own gravity. At the surface of the star, the pressure is 0 and is maximum at the center of the star. So, here the cartoon depicts that at the center the pressure is 0, and while at the center of the star the pressure is maximum. Then we will also encounter some term like stellar opacity. The removal of photons from a beam of light travelling through a gas is termed as absorption. Absorption includes scattering of photons such as Compton scattering, as well as true absorption of photons by atomic electrons making upward transitions. The opacity of a star is a factor which determines how radiation diffuses from the interior to the outwards of the star. Mathematically, it is defined as the cross section for absorbing photons of wavelength lambda per unit mass of the stellar material. It has the units of meter square per kilogram. In general, the opacity of a gas is a function of its composition, density, temperature and is wavelength dependent. It is denoted by kappa lambda. Now, we will study how we can build up a simple model for pulsating stars. So, the simple model of pulsating star was given by Sir Arthur Stanley Eddington, who proposed that the radial oscillation of a pulsating star may be the result of sound waves propagating in the stellar interior. Now, a rough estimate of the pulsation period can be easily obtained by the length of the time it would take a sound wave to travel across the diameter of a star of radius r and constant density rho. So, therefore, the period capital P is twice r divided by V s, where V s is the adiabatic speed sound given by square root of gamma p divided by rho, where rho is the pressure and gamma is the ratio of the specific heats of gases of the stellar material. The pressure may be obtained from the equation of hydrostatic equilibrium given by dP by dr is equal to minus g m r rho divided by r square. Here m r is equal to 4 pi by 3 r cube rho, and this can be written into dP by dr is equal to minus 4 pi g r rho square divided by 3. Now, integrating the above equation using the boundary condition that the pressure at the surface is equal to 0, then we can write the pressure as a function of r given by this expression 2 by 3 pi g rho square capital R square minus small r square. Thus, the pulsation period is roughly given by 2 into 0 integration 0 to r V s dr by V s, and this integration can be solved to find capital P is equal to square root of 3 pi divided by 2 gamma 0, and so therefore, the period goes as 1 by square root of the mean density. It goes inversely as the square root of the mean density. This relation is known as the period mean density relation, and it shows that the pulsation period of a star is inversely proportional to the square root of its mean density. Although the derivation is not so much rigorous, however, it produces period estimates for classical Cepheids that are in good agreement with the observations. Now, we can derive the same equation by using the virial theorem. So, we know that the kinetic energy is given by 3 by 2 n k T. Now, this capital N is the number of molecules of the gas, K is the Boltzmann constant and T is the temperature. This n k T can be replaced with a P into V, where P is the pressure and capital V denote the volume. This comes from the kinetic theory of gases, and this can also be written in terms of a quantity called the mean molecular weight, and the pressure can be written as rho k T divided by mu m h, where mu is the mean molecular weight and m h is the atomic mass of hydrogen. And from here we can find P by rho is equal to k T divided by mu m h. Now, the gravitational potential energy of a star can be written as g m square by r. Now, applying the virial theorem, which says that 2 times the kinetic energy is equal to the potential energy. Now, we put the values and after that we find that square root of gamma p by rho is equal to square root of gamma g m divided by 3 r, and since this square root of gamma p by rho is nothing but the speed of sound in gas. So, this is equal to square root of gamma g m divided by 3 r. Therefore, the pulsation period is given as capital P is equal to twice r by V s. So, we have got P is proportional to square root of r cube by m, and this density goes as mass per unit volume. So, therefore, we can write down P as 1 by proportional to 1 by square root of rho. Now, this is the mean density relationship, and we can see that both of them are same when we are approximating that by using the Eddington approximation. Now, the next question is important. The next question Eddington take up is that why do stars pulsate? And Eddington used the mean density relationship, and he found an answer that why do some stars pulsate. So, now we start with the period mean density relationship, and period mean density relationship P goes as 1 by square root of rho. Now, from here we can see that when the density increases, pressure decreases, and that is why if we go into the look into the Hertzsprung-Russell diagram, and if we move from move in an instability strip from the very tenuous supergiants to the very dense white dwarf, the period, the pulsation period decreases, because in the case of supergiant the density is very low, whereas in the case of the white dwarf the density is very high. Now, let us consider that suppose a layer in the outer part of the star contracts for some reason due to some momentary loss of hydrostatic equilibrium. Now, we know that the gases inside the layer, they will be heated up, and once they become heated up, then we know that they become much more opaque to radiation. They become much more radiation. Radiation diffuses more slowly through the layer because of its increased opacity, and heat builds up beneath it. Pressure rises below the layer and eventually starts to push the layer out. The layer expands, cools, and becomes more transparent to radiation. Energy can now escape below the layer, and the pressure beneath the layer drops. The layer falls inwards and the cycle repeats. Now, very importantly, that in order to have this, we need a mechanism by which the pressure opacity increases as temperature increases. But Kramer's law of opacity, it says that kappa, or the opacity, goes as rho by T to the power 3.5, and therefore, when the envelope is compressed, then the opacity decreases on compression. There are certain zones within the star which are known as the hydrogen and helium partial ionization zones, and in those zones the temperature does not increase much on compression. Since the energy of compression goes into fully ionizing hydrogen and helium, and hence the density increases. So, there is very little change in temperature, but the density increases, and that increases the opacity. Similarly, during expansion, temperature does not decrease so much, as the ions release energy when they combine with the electrons, and the density decrease, and so does the opacity. This is known as the kappa mechanism. Now, there exists a temperature gradient between the partial ionization zone and the surrounding layers. The surrounding layers are at a higher temperature as compared to the partial ionization zone, and because of the temperature gradient, the more heat flow diffuses into the uh, ionization zone and which causes more ionization. This is called the gamma mechanism and it reinforces the kappa mechanism. Now, here is one these are the sequences of steps in which this kappa mechanism works. Eddington bulb mechanism, Eddington analogy was that the stellar envelope acts like a heat engine with the radiation taking part of the stream, the expanding and the contracting layer acting as piston and the opacity of the layer acting as the bulb mechanism. Now, here shows some of the step. Let us say a layer of stellar material loses support against the star gravity and falls inward. So, this is the layer and this layer of the star it falls inward due to some momentary loss of hydrostatic equilibrium, and this inward motion tends to compress the layer which heats up and becomes more opaque to radiation, and the layer is compressed, the gas within the layer is heated up and it becomes more opaque to radiation. Now, the radiation diffuses more slowly through the layer as a consequence of increased opacity, heat builds up beneath it. So, because of the increased opacity in these layers, the radiation is trapped inside and pressure within the layer increases. So, at one point of time the pressure rises in such a way that it pushes the layer outwards. So, as the layer is pushed outward, its layer expands, cools and becomes more transparent to radiation. It becomes more transparent to radiation. Energy can now escape from below the layer and the pressure beneath the layer drops. So, the energy because of the decreased opacity when the layer is pushed up, now this energy can flow outside, and as a result of that the pressure within the layer decreases and again the star falls inwards and the cycle repeats. Now, very importantly, that location of partial ionization zones. This location of partial ionization zones, partial ionization zones are also known as Zhivakin zones in the name of Russian scientist S. Zhivakin. He said that within the star there are some partial ionization zones, and this the location of the zones determine the pulsation properties. For stars hotter than 7500 degree Kelvin, the partial ionization zones are located too close to the surface. So, here in this case in the left figure we can see that at a temperature of the order of 7500 degree Kelvin, these partial ionization zones are located close to the surface of the star, where there is not enough mass to drive the oscillation. This accounts for the blue edge of the instability strip. Similarly, for stars cooler than 5500 degree Kelvin, the partial ionization zones are located deep in the stellar interior. At low temperatures, energy transport via convection becomes much more effective in the stellar interior, preventing the buildup of heat beneath the driving pulsation layer. This accounts for the red edge of the instability strip. Now, there exists a very important relationship between the luminosity and the hydrogen ionization zone of a pulsating star. The maximum brightness of a pulsating star occurs when least mass lies between the hydrogen ionization zone and the star surface. As a star oscillates, the location of an ionization zone changes with respect to both its radial position r and its mass interior to r, denoted by m subscript r. Although the energy beneath the layer beneath the ionization layer peaks when the star's radius is at a minimum. This energy propels the hydrogen ionization zone towards the star surface. The observed luminosity of the pulsating star is thus at a maximum slightly after the star has been compressed to its smallest radius. Now, we will discuss about radial pulsation in case of a radially pulsating star. In radial pulsations, the star remains spherical and simply changes its volume radially in and out. A star is analogous to an open organ pipe that is open at one end. A node exists at the center of the star and an antinode at the surface. For the fundamental mode, the gases move in the same direction at every point in the star. For the first overtone mode, there is a single node between the center and the surface, with the gases moving in opposite directions on either side of the node. Similarly, for the second overtone mode, there are two nodes between the center and the surface, with the gases moving in the opposite directions on either side of each node. Vast majority of the RLE rays, classical Cepheids and Mira variables pulsate in the fundamental or first overtone modes. Some of the RLE rays are found to oscillate in both the two modes simultaneously. Here is a schematic illustration of the node lines in the stellar interior for a radial pulsation with n is equal to 2. So, n is equal to 2, it says that there are two nodes in between the center and the surface of the star. In non-radial pulsation, the motion is not along the radii, and some parts of the stellar surface move inwards while some move outwards, or the star changes shape while keeping its volume essentially constant. Non-radial modes are characterized by the number of surface nodes, which are lines of movement as in any vibrating system. The degree L indicates the total number of nodes on the surface, and m the number of running through the pole. This is an illustration of pulsation pattern for an oscillation with L is equal to 3. The yellow colored surfaces move outward, while the blue colored ones move inward. Also, the movement of the node line is illustrated. Here is an animation of non-radial pulsations, where the different parts of the star move in and out in different directions. Non-radial pulsations are also classified into P and G modes, and these two main sets of these are two main sets of solutions to the equation of motion of a pulsating star. And for P modes, the pressure is the primary restoring force perturbed from the equilibrium. These P modes are acoustic waves and have gases which are moving in vertical directions. For the G modes or gravity modes, buoyancy is the restoring force and the gas motions are primarily horizontal. Radial modes can be viewed as a special case of non-radial P modes with L is equal to 0. Pulsation periods with periods longer than that of the radial fundamental mode are usually G modes, whereas P modes have periods equal or shorter than that. The P modes mainly attain a large amplitude in the outer layers of the star, while G modes have a large amplitude in the deep layers of the star. Corresponding periods of G modes are one order of magnitude longer than those of P modes. For massive main sequence stars, P modes have periods of the order of hours, while the periods of G modes are of the order of days. Now, we will discuss about the pulsating star, beta Cephei and slowly pulsating B variables. Variability is common among B stars. The beta Cephei stars and the slowly pulsating B stars are two of them and are found in the upper part of the main sequence. Beta Cephei stars are low order P or G mode pulsators. Their pulsation periods are of the range of 2 to 12 hours. They belong to early B type stars, and their spectral type is from B1 to B3. They are massive, masses go from 7 to 20 solar masses, and their temperatures are very high, of the order of 18,000 to 35,000 degree Kelvin. Slowly pulsating B stars are high radial G mode pulsators. Their pulsation periods go from 0.5 to 5 days. They belong to mid to late B type of star, and they are very massive. Their masses range from 3 to 8 solar masses, and also they are very hot. Their temperatures go from 10,000 to 20,000 degree Kelvin. Here is an example of a beta Cephei star, and there are 4 light curves shown for 4 stars, 4 beta Cephei stars. These are taken from Pigulski and Pozmansky, and these stars were discovered from the ASAS data. ASAS belongs to ASAS is basically it is a ground based survey called All Sky Automated Survey. Now, here is a light curve of a slowly pulsating B stars. This stars you can see they can have a large number of modes. They are multiperiodic. Now, we have the pulsating stars like rapidly oscillating AP stars. They are a subtype of AP star. They are chemically peculiar that exhibit short time scales, rapid photometric or radial velocity variations. The known period range from 4 to 21 minutes. They have a strong magnetic field of the order of 1000 Gauss and chemical peculiarities with non-uniform distribution both horizontally and vertically. Their rapid oscillations are interpreted as high overtone, low degree, non-radial P modes. They lie in the delta Scuti main stability strip on the main sequence. The driving mechanism of their oscillation modes is still a matter of debate, but the most probable explanation seems to be the kappa mechanism acting in the neutral ionization zone of hydrogen. The first Rope star HD 101065 was discovered by Donald Kurtz using the 20-inch telescope at the South African Astronomical Observatory. An amplitude variation of 10 to 20 millimag in the light curve of the star with a period of 12.15 millimag was observed for the star. Gamma Doradus variables are pulsating stars which are bright and early F type dwarfs. Masses range from 1.5 to 1.7 solar masses. These stars have typical periods between 1 and 5 periods ranging from 0.4 to 3 days with the photometric amplitudes up to 0.1 mag in Johnson V band. The mechanism for this observatory variation is high order, low degree, non-radial gravity mode pulsation. Here shows the light curves of Gamma Doradus stars, which are asymmetric light curves, and there are five stars which are taken from the Kepler data. Delta Scuti stars. Delta Scuti stars are short period pulsating variables located in the lower part of the classical instability strip on or above 0 age main sequence in the HR diagram and have masses ranging from 1 to 3 solar mass. The typical time scales of oscillations range from 18 minutes to 8 hours. Since the time scale of oscillation of this class of stars is short and since they are bright, the time sampling of the light curves is of the order of few tenths of seconds and requires fast photometry. These variables are spectral type A to F dwarfs or subgiants that have not yet reached the red giant branch and hence are mainly moderately evolved objects. The majority of these variables pulsate with very low amplitudes ranging from 0.1 mag to several tenths of a mag in the V band with non-radial, low degree and low order P modes. Some are radial pulsators and some others also pulsate in a mixture of radial and non-radial modes. Delta Scuti stars are divided into two main types, the high amplitude delta Scutis HADS and low amplitude delta Scutis, namely LADS stars. High amplitude delta Scuti stars have photometric variation of more than 0.25 magnitudes. They pulsate primarily in the radial modes and have higher amplitudes. Conventionally, with the V-band amplitude less than 0.30 mag and have more stable light curves. Some of the high amplitude delta Scuti stars may have non-radial pulsation modes present. The light curves are generally asymmetric with the rise time from a minimum to maximum light being short as compared to the decline time from the maximum to minimum light in the same sense as Cepheids and RRAB type stars. Here are some examples of high amplitude delta Scuti stars. On the other hand, low amplitude delta Scuti stars have small variations on the order of millimag. They typically pulsate in the multiple modes and often have non-radial modes. Delta Scuti stars are often considered to be the short part counterparts of the classical Cepheid excited by the kappa mechanism. These are some typical light curves of low amplitude delta Scuti stars.